Deep beneath the Earth's surface lies a swirling molten core. This movement generates a complex magnetic field that erupts outward, wrapping around the rotating planet. Mastering the disconnect between this chaotic, invisible field and the static maps we use to navigate is a mandatory foundation for DGCA general navigation and practical aviation safety. To navigate accurately, we first rely on true direction. This is defined strictly as straight lines relative to the Earth's geographic north and south poles, the fixed axis upon which the planet spins. A compass, however, detects magnetic north. The complication is that the Earth's magnetic poles do not perfectly align with its geographic poles, nor do they sit directly opposite each other on the globe. They are not perfectly antipodal. Therefore, pilots cannot blindly follow a compass needle. To fly safely, you must systematically correct for the planet's geometric imperfections. This map illustrates variation, the precise horizontal angular difference between true north and magnetic north. The amount depends on the observer's relative geometric placement to these poles. Where these paths perfectly intersect is an agonic line, resulting in exactly 0 degrees of variation. This entire system is in motion. Because the magma generating this field is constantly swirling, the magnetic poles drift over time, moving by approximately 22 nautical miles every year. Variation is an unavoidable, ever-shifting geographic reality. As the poles migrate, variation changes, making periodic mathematical updates to aeronautical charts essential for survival. This map displays isogonals, dashed lines connecting places with the exact same magnetic variation. Notice how they converge dramatically near the poles, creating a highly complex and rapidly changing magnetic environment for navigators at high latitudes. This diagram shows where this complexity reaches its mathematical limit. If an aircraft's position falls exactly on the line between the magnetic pole and the true pole, the angular difference hits a maximum variation of 180 degrees. At these extreme polar latitudes, standard magnetic navigation becomes completely mathematically inverted. A magnetic compass is useless here, necessitating alternative true heading navigation systems like inertial references. Geographic offset is only the horizontal component of the problem. As we navigate the Earth's magnetic field, we must also correct for a vertical error known as magnetic dip or inclination. This cross-section diagram shows the Earth's magnetic flux lines in 3 dimensions. We geometrically decompose these vectors into a vertical component and a horizontal component. This horizontal vector is directive force, the energy pulling the compass needle toward magnetic north. Approximately halfway between the poles lies the magnetic equator, or the aclinic line. Here, the angle of dip is exactly 0 degrees. The vertical element is nil, meaning directive force operates at its absolute maximum efficiency. But the nearer an aircraft gets to the magnetic pole, the greater the vertical component becomes. The compass needle is violently dragged downward, physically scraping against its casing as extreme vertical magnetic forces override the horizontal pole. Eventually, as the aircraft approaches a magnetic pole, the horizontal directive force decreases until it drops below the standard 6 microtesla operational threshold. At this exact geometric point, magnetic compasses are rendered physically useless. Even if we perfectly account for variation and dip, there is a third error. We must shift our scope from massive planetary phenomena down to the highly localized, metallic environment of the commercial aircraft cockpit. An aircraft is packed with metal, radios, and communication panels, and electrically driven instruments. These all generate their own localized magnetic fields that actively interfere with the Earth's natural magnetic flux. This schematic demonstrates how this interference creates compass north. This is a corrupted heading. It is not a real geographic place. It is merely magnetic north, warped by localized magnetic sabotage. We define this specific angular difference between the true direction of magnetic north and the corrupted compass north heading displayed to the pilot as deviation. Deviation is a dynamic error. It changes depending on the aircraft's current heading relative to its internal magnetic fields, and the resulting distortion is completely unique to each individual airframe. Because this error profile is entirely unique, licensed engineers must periodically swing the compass on the airport tarmac. They rotate the physical aircraft through different headings to calculate and meticulously tabulate its exact deviation. Even a master of planetary geometry will veer dangerously off course if they fail to correct for the invisible, localized interference generated by their own machine. How do we correct for this in practice? The navigator's operational objective is converting a plotted true map course into a flyable compass heading. This digital display outlines the sequential mathematical pipeline. Start with the true heading, apply local variation to find the magnetic heading, and finally apply the aircraft's specific deviation to find the compass heading. To correctly add variation when moving from true to magnetic, aviators use a standard DGCA memory aid. Variation west, magnetic best. This means you add a westerly variation. Conversely, we use the inverse subtraction rule for easterly variation. Variation east, magnetic least. Here, you subtract the variation value. You then apply the exact same logic pipeline to correct from magnetic heading down to the final compass heading. Deviation east, compass least, meaning you subtract an easterly deviation. Rigid, disciplined application of these arithmetic rules is the only reliable defense against the compounding errors built into the Earth's magnetic architecture. Let's review the precise definitions of these three distinct errors. Variation is the geographic horizontal offset between true and magnetic north. Dip is the latitude-based vertical pull of the magnetic flux. And deviation is the localized magnetic interference occurring entirely within the cockpit. Remember that while true north is a geographic absolute based on planetary rotation, magnetic and compass headings are dynamic, inherently flawed systems that require continuous pilot vigilance. Mastering this exact geometric framework is a critical requirement for both DGCA examination success and real-world flight safety. Precise flight depends on the continuous, calculated deconstruction of the planet's invisible forces.